All right. Hey, everybody. It's Brian. We're going to be looking at the fundamental theorem for line integrals today, which is essentially it's a generalization of the fundamental theorem of calculus. So this is based on the idea of a line integral, right? So we have we're letting C be some smooth curve given by a vector function r of t. So the function has t going from the curve is t is going from a to b. Okay, so here's our curve, right? So here's where t equals a, t equals b, and t kind of goes in that direction. This is our curve C. So if f is a differentiable function of 2 or 3 variables, and it's got a gradient vector gradient f, if that's continuous on C, then the integral of the gradient of f dot dr is equal to the function f evaluated at r of b minus the function f evaluated at r of a. You can see that if f is actually just a function of a single variable, then this actually becomes the fundamental theorem of calculus if you simplify f to be a function of just one variable. And so what we get now is another theorem that falls out of that, we say that some line integral is independent of path on some large domain D, if and only if the for every closed path on D, the line integral is always going to be 0. So if you can see what that means, right? That like here's one closed path, C1. If we're starting at and ending at the same point, then this would be like R of A. If R of A equals R of B, so if this is if doesn't matter what curve we follow, that if the closed path line integral is always 0, then the line integral is independent of path. Likewise, if it's independent of path, then that means that the line integral over every single closed path is always going to be 0. So if we have some vector field f that's continuous on an open connected region in D. So when I say open connected, so here's actually an open region does not contain the boundary, and connected means that you can go from you can kind of draw a path from any one point in D to any other point in D, and you can get there without leaving the region, right? So connected is exactly what you think it would be. If you this would not be connected, and if something like this would not, although you could see that they're kind of touching, because it's got an open boundary, it's not open and connected, because you can't go from this point to this point to here, and here you like have to leave the region because the point where those kind of dotted lines intersect is not in the domain. So anyway, as long as you are on an open connected region in D, and if you have some line integral that is independent of path, if line integrals are independent of path on D, then that means that f is a conservative vector field. Remember, a conservative vector field means that you can always find some potential function f such that capital F is the gradient field for that potential function. So if every line integral is independent of path in D, then f is a conservative vector field. So you might be wondering, well, if it's a conservative vector field, is every well, this is the flip side to what we had before, right? We already know if it's a conservative vector field, then every line integral is going to be independent of path. But this is some conditions on the region being open and connected. All right, so here we're going to look at the case where if we have f as, we're looking at a two-dimensional vector field f, where we can write it as p of xyi plus q of xyj. So if this vector field is a conservative vector field, and P and Q, where P and Q have continuous first order partial derivatives on domain D, then everywhere on D we have the case that the partial derivative of P with respect to y equals the partial derivative of Q with respect to x. And so this is leading us to a kind of a test for whether or not a vector field is a conservative vector field. And so, but this is a test that can tell you if it's not a conservative, this can tell you if a vector field is not conservative. But if this is true, this theorem doesn't tell you, this is not a two-way street, right? If this is true, it doesn't necessarily mean that the vector field is conservative. For that we need this additional condition, right? So this is the theorem that has that condition. So if we have a vector field, right, capital F, that's Pi plus Qj, if it's a vector field on an open and simply connected region D, okay? And when I say it's simply connected, basically there's no, when I say it's simply connected, we need to, to give you a sense of what we're talking about, simply connected means there's you could basically, there's no, it's all connected. So that's the first thing, is that you can get from any one point to another point without leaving it. So it's not simply connected if it is composed of two kind of separate regions, but also no holes are allowed in a simply connected. So this would not be simply connected. There's no little tiny holes are allowed. So as long as the vector field is on an open simply connected region D, and as long as if P and Q have continuous first order partial derivatives, if partial P with respect to y equals partial Q with respect to x everywhere, then F is conservative. So there's your check to see whether a vector field is conservative. So here's an example. Now, this example, F is this everywhere on, this is defined on all of R2, and there's nowhere where this is undefined. So all of R2 is open and simply connected. Okay, so we want to determine if this is conservative. So P is x minus y, Q is x minus 2. So partial P with respect to y is negative 1, and partial Q with respect to x would be 1. And so this is not conservative because negative 1 does not equal 1. That's it. This is the check to see whether or not it's conservative. It's not conservative because those two partial derivatives are not equal to each other. And actually, let's take a look at what this vector field would look like. So this is what this vector field would look like, and it's not conservative. And actually, once you get a little bit of practice, you can tell it's not conservative just from looking at the vector field. Whenever you have these kind of swirls, vortices, and stuff, you can see that that's an indication that it's not a conservative vector field. For example, if you can plot a couple paths from, say, some starting point, let's say if I was going to go from here to here, if I go straight down this way, The integral, because I'm moving perpendicular to all of these vectors in the vector field, that's going to have a line integral of 0. But if instead I was to travel in the kind of direction of things, more or less, then you're going to not have a 0 for your line integral. And likewise, you could see if you went in the other direction, you'd be going against the grain, and so the line integral would have the opposite sign. So, you can see, like, when you have a spiral like this, it's not going to be conservative. Also, you could think of it like, how could there be a landscape where this is showing you the gradients over that landscape? How could you be going uphill in a spiral and then end up walk in a circle, keep going uphill, and end up at the same point you started at? That wouldn't make any sense at all, right? Let's take a look at this one. Determine if this vector field is conservative. If so, find a potential function f for it. Well, let's find p of x, y is 3 plus 2xy, and then q of xy, that's x squared minus 3y squared. Well, the partial p with respect to y, this is going to be 2x, that's straightforward. The partial q with respect to x is going to be 2x also. Ah, look, this is conservative. Again, I didn't mention it. The check is this is defined everywhere on R2. So it satisfies the conditions for that theorem. These partial derivatives are going to be equal to each other everywhere on its domain, which is open and simply connected. Now, to find a potential function for this, we need to, so f of x, y is going to be the integral of so p of xy, 3 plus 2xy dx. If you integrate that with respect to x, and it's also going to be the integral of x squared minus 3y squared dy. Okay, so what are these integrals? This is going to be 3x plus x squared y plus g of y. So because if you took the derivative with respect to x, any function of y would be wiped away. On the other hand, if you integrate this this q of xy with respect to y, you're going to get x squared y minus, that's going to be y to the third, and then plus any other function of x would have been wiped away when you took its derivative with respect to y. So now we look at these side by side and we see, can we match things up? Can we make it work? Well, you can see x squared y is common to both of these, so that's fine. So f of xy has x squared y in it. Now, what's different on the two sides? You have a 3x on this side, and we have some unknown function of x on the other. That works. So we can just have plus 3x. And then the other thing is you have to have, and any function of y would work, and then we have minus y cubed. That's the missing piece. This is a potential function of f. We say a potential function of f because really you could add any constant to this and it would still be the potential function. The partial derivatives would still match up because that simple constant would be wiped away for all of the partial derivatives. It's asking for just a potential function, and this is good enough. Now let's take a quick look at what this vector field looks like and see what a conservative vector field. So you can see for this vector field, you don't have any eddies or spirals. And it turns out, if this can represent the gradient for some landscape. So you could see if you're starting at one point, and if we're going over to this point here, it kind of doesn't matter in which direction we go. The net amount of change in altitude is going to be the same no matter which path we take, right? That's the idea for a conservative vector field, and one interpretation of this fundamental theorem for line integrals. So let's take a look at this one. We have now three-dimensional, but the idea is exactly the same for. So here, what we want to do is just try to find its potential function. Let's try to see if we could figure out what a potential function would look like. So we're looking for some function f of x, y, z, right? And this, if we were to integrate each of these, so let this be our p, this is our q, and this is our r. If we are into f of x, y, z should generate this vector field, such that if we take the derivative of the partial derivative of f with respect to x, we'll get y squared. So we're going to say that this integral of y squared dx should be my original function. But also, if we were to integrate 2xy plus e to the 3z dy, you should get back to the original function f. Also, if you integrate 3y e to the 3z dz. So what are these? What are all of these? We're going to have integral of y squared with respect to x is going to be x y squared plus some function. I'm going to call it g of y z. So any function of y and z would have been wiped away when we took the derivative, the partial derivative with respect to x. On the other hand, if we integrate 2xy plus e to the 3z with respect to y, we're going to get xy squared plus y e to the 3z plus some function, I'll call it h of x and z, which would have been wiped away. Now if we take the derivative of 3y e to the 3z, you can see that's actually going to be y e to the 3z, integrating that with respect to z, plus I'll say some function, call it k of x and y. Any function of x and y would have gone away when we took the derivative. Now, you can see what's common to all of these, right? We've got x to the y squared, or so xy squared, and xy squared. Okay, so those are in both of these. So this is a function of x and y. I'm going to say that's xy squared is my k of xy. Then we've got this y e to the 3z is here and it's here. Well, that's a function of y and z. So that's going to be my y e to the 3z. And then I've got it made. I really don't have to have anything. I can have this h of xz simply be 0. And so in the end, f of x, y, z, a potential function, there's others that could work, but x y squared plus y e to the 3z plus nothing, right? That's all I need. That's a potential function. This is going to generate this vector field, this conservative vector field. So we've found its potential function, so we've proven that it's a conservative vector field. So you don't have to use that theorem. If you can find the potential function, it's a conservative vector field. Let's use the fundamental theorem of line integrals to evaluate a line integral without actually evaluating it, doing the integral. So my f here is xy squared I plus x squared y, x squared y j. Okay, so I'm going to integrate xy squared dx. This is going to give me 1/2 x squared y squared plus some function of y. And the integral of x squared y dy is 1/2 x squared y squared, okay, plus some function of x. But it turns out that my function of y and the function of x must be zeros because there's no way for, well, or a constant, right? Because there's nothing, any function, any g of y that has any y's in it couldn't exist because that would have to be here someplace. The only thing that's missing is a function of only x. So f of xy, I'm going to use 1/2 x squared y squared. Now to integrate the integral of c of f dot dr, my function, this is by the fundamental theorem of line integrals, this is f of r of a, comma, sorry, it's f of r of b minus f of r of a. Okay, so what is r of a? When a is 0, right? This is our starting value, and our ending value is 1. So r of a is that's 0 plus the sine of 0, and then 0 plus the cosine of 0, which actually is simply going to be 0, 1. And r of b, this is going to be 1 plus the sine of 0.5 times pi over 2 times 1. That's going to be pi over 2. And then we have 1 plus the cosine of pi over 2, which is going to be, the sine of pi over 2 is 1, so it's going to be 2, 1. Okay, so f of 2, 1, well, it's what I'm finding is f of 2, 1 minus f of 0, 1. So this is going to be 1/2 2 squared times 1 squared minus 1/2 0 squared times 1 squared. Well, okay, that's just gone. 1/2 times 4, that's going to be a 2. And that's what this comes out to be. So this is how you can, so if you can find a vector field is conservative, then you can use the fundamental theorem of line integrals to calculate the line integral, and it makes things a lot easier. That's the bottom line. No pun intended. All right.